All right, Karl, also a Microsoft person, will compare and contrast C++ concepts with type classes from functional programming languages. As a program manager on the Visual C++ front-end team, he's interested in type theory and language design. And later, you guys can teach me how to be on the right page in an Office document. Go ahead, Karl.
Okay.
5 minutes. For concepts and type classes, 5 minutes.
What is this? F5. Whoa.
There you go.
There we go. Okay, so my talk is called Convergent Evolution because it is about oh wow, I don't want this. You don't see it, but there's a Wi-Fi hotspot thing on the screen. Oh, dang it. Okay, decline. Anyway, let's talk about now, it's not anything new. If you read the papers, most of this information it's already been pointed out elsewhere. But I just thought it was a cool idea. I think it's a cool idea, and I want to show you guys how cool it is. And it might help you, think about your programs in a different light. And I think it demonstrates that when there's a design problem, and if you try to solve the problem right, everybody comes at the same solution for it. So start out with the well-known fact that programs are proofs. They call this the Curry-Howard correspondence. Basically what it means is types are propositions or statements of whether it's true or false. And an object with that type is a proof of the proposition that that type represents. Now, of course, this is not true in any real-life programming system, especially not C++, because C++ is messy. There's evaluation schemes to think of. There's side effect. There's cosmic rays and come in and mess up your memory bits for you. It's not a very neat system, but it's fun to think of it like that sometimes. And I think, it's my opinion, that this idea ties every programming language in the world together in harmony. Now, what does this mean? Very kind of a rough interpretation of the types in C++ are that you got functions. Functions are implication, which is why in Haskell it uses arrow. Any sort of aggregate is and. Obviously, you want two values together, you need both. Some types, unions, Haskell has algebraic data types. These are either-or situations, and that's why they're or. We also have parametric polymorphism. It's for all. Haskell has for all explicitly. You can write for all. In C++, you got to use templates. Existential types are complicated, and I will not be talking about them. But if you read types and programming languages, apparently there are pairs of values and types together. I'll leave it at that. Now, bear with me for a second. What exactly is a constraint? If you think about it, let's go with an example. You say you want to sort a set, right? And you got to prove that the elements of that set have a total order. Now you got the qsort function from C. If you look at that, there's a compare function there that takes two void stars and returns a greater than, equal to, or less than. And here, that is the proof by the definition of total order. It proves that there's a total order on the elements of the set. It's a constraint on the elements of the set. Yes, once again, since we're talking about a C language, not like a pure functional thing. It's a very rough approximation, but essentially a constraint is just an extra parameter, right? Your lemmas in your proof. So why are there concepts and type classes? Why? Convenience, of course. I mean, if you really think about it, all they are, we can program in a way that if you want to provide proofs for something, you just pass it in explicitly, right? But we don't want to do that all the time. If you have an established fact about a type, if you know something, you want to be able to just say it once, tell the compiler, hey, this is known about these things, and every time I mention this constraint, well, bring it up for me. You're telling the compiler to, who here knows what JFGI stands for? Just get it from the environment for me, please. I don't want to supply that proof every time I want to sort a set of T objects if I already told you that T has a total order. And this is like, it's very interesting because in Haskell and in Scala, type classes are implemented in terms underneath. They're implemented with implicit parameters. They are implicit parameters. They're implicit parameters that are indexed by the type. And yes, type classes are a type of a different kind than the normal types you deal with, but they're still a type nonetheless. And by mentioning the type class, by mentioning the type, you're indexing into that the thing you've told the compiler already, and you can bring it out. Here's a record of these methods, and you use them directly. So that's what they are. Concepts and type classes, they allow you to state facts about types in a single place, and then those facts are now known everywhere just by mentioning the constraint. Now, of course, every time people bring up concepts, they go, oh, we want to simplify template errors, and that's nice and all, but the more theoretical, I'd like to think of it this way. It tickles the functional programmer in me. So if you drink the Kool-Aid, here's what stuff looks like. And this is, to the left is actually it is what Haskell libraries have. You have a sort function, it sorts a list that equals greater than. That's the arrow that tells you that things on the left, that's the constraint. So you have an ord. If it's ordered, well, order requires that you be able to sort something, a bool, it's a less than or equal to, and then that, of course, requires an equality thing. And translate that into C++, you got, I hope I got the syntax right for that one.
It looks good.
Thank you. Thank you very much. So that's it. So I have one more question for you guys. Was this well-known information before I brought it up here? Is this like, do any of you guys already think of constraints in such a way?
No, because I didn't program in Haskell. So.
Yeah, I have a coworker who is quite the Haskell guy, so I see this occasionally.
It's good to know. So yeah, further reading, if you got time, type classes as objects and implicit. It's a very good paper, Martin Odersky. Of course, people already, like I said, there's a paper already on comparing Haskell type classes and generic programming in C++ with concepts. And that's it. That's my talk.